On behalf of the Council of Deans and our entire academic community, I would like to extend my warmest congratulations to your honorary doctorate. The university is delighted and proud to have such a distinguished scholar and professor as honorary doctorate holder. I invite you now to take the floor.
Well, thank you very, very much. It's a true honor and great delight to be here, to be part of your celebrations, and also to receive this honorary doctorate. I'm especially pleased to be honored like you in this fashion, and I'm going to try and explain why, but I will explain why I'm particularly pleased to be here at the end of my presentation. I have been preoccupied by a number of themes in the brain sciences and neuroscience over my career. And some of those themes your university has a passion for and has contributed to in a very substantive and admirable way. I'm going to focus on one of them. So my job is to tell you what I've been doing and reflect what you have been doing in part. So I've chosen to focus on the notion of predictive processing and the Bayesian brain. And it picks up on many themes that we've been hearing about in the earlier presentations today. The idea here is that our brains are fantastic organs. They are literally purveyors or generators of fantasies or hypotheses that explain our sensory impressions. So they're statistical machines building explanations for what we see and hear and perceive. And this idea is beautifully articulated by Helmholtz here. Objects are always imagined as being present in the field of vision as would have to be there in order to produce the same impression on the nervous mechanism. So this is clearly very closely related to the ideas of psychologists like Richard Gregory, who treat perception as hypothesis testing. It gave rise to great advances in machine learning, pioneered by people like Geoffrey Hinton and Peter Diane, such as things like deep learning, borrowing from the notions of Bayesian probability theory and finessed mathematically by contributions from people like Richard Feynman, in particular variation-free energy formulations. So a perfect storm, speaking to something which we can all do and which we indeed treasure. Let me just illustrate. Let me actually ask again for the second time in half an hour. Look at this picture, and what do you see? Ask yourself, what do you see? Do you see a bowl of vegetables, or perhaps the vegetable gardener? Now, if you see that, that comes from inside out. That is part of your ability to build an explanation for these visual inputs. So as you're smiling to yourself, you are admiring your own fantastic organs. The idea now, or the challenge, is to understand how does the brain do that. There has been remarkable progress over the past 10, 20 years, understanding the forms and the ways that we map from the consequences of the causes of our sensations back to those causes, and thereby work out and infer what actually caused our sensory input. So this notion of sensory impressions, I think, is a very beautiful one. Imagine that you received shadows from your sensations on your sensory epithelia, and that's all that you had. That's the only access that you had to the world. And your job then, or the brain's job, is to try to work out beyond the veil, hidden behind the sensory curtain, what caused those shadows. And that's the problem of the Bayesian brain, or the inversion of models mapping from causes to consequences to get back from the consequences to their causes. And much work points to the notion of the brain as using predictive coding or predictive processing to solve this problem. So very briefly, I'm going to explain what that is and why it has been such a useful vehicle to understand message passing in the brain. In essence, we consider the brain, neural activity, connection strength, wiring connection strengths in the brain to represent or encode beliefs, hypotheses, expectations about what are causing the sensory impressions. And the way that it does this, the way that it updates its beliefs, it optimizes its expectations about the world that is hidden behind our sensory veil, is to minimize prediction error. Now, I've written that down mathematically in a number of ways which will appeal to the mathematicians and the engineers in the room, and will probably do little for anybody else. Suffice to say that there's a deep mathematical backstory to this that relates to notions such as Kalman filtering, predictive coding, and Bayesian filtering. But I just want to focus on the intuition here. Let's suppose that you had access to this visual impression, this shadow. Now, you might try to explain that in terms of an expectation, say that it was caused by a howling dog. And if you had a model or a process that would generate the sensory consequences that you would experience if indeed a dog was causing your sensory impressions, then you would have a prediction here, a function g for a generation process of my expectation mu. And one could simply subtract what we see, what we receive, from what we predict we would if our hypothesis was correct. And the residual or the mismatch is a prediction error. Therefore, it is sufficient in order to infer or explain, get the best explanation, it is sufficient to minimize prediction error. And all that equation at the top says is that we just change our beliefs in order to minimize our prediction error using something called a gradient descent. Now, I use the word sufficient advisedly and deliberately because if we can go through life avoiding surprises, avoiding anxieties, avoiding uncertainties, at every point minimizing our prediction error, that is entirely sufficient for a good life. It does not have to be a life in which we actually know the true causes of our sensations. It is only necessary to minimize the prediction errors. And that provides a very nice and simplifying perspective on much of neuroscience, much of psychology, systems neuroscience, in terms of action and perception. So we can consider both in the game of minimizing prediction errors, but in fundamentally different ways. First of all, we can either change the internal states of the brain, our brain activity, our connection strengths during learning and during development, in order to make our expectations, our hypotheses, or beliefs about the world produce predictions that are more like the sensations that we actually receive. And we can associate that with perception. But there is another way that we can minimize prediction error. We can simply change the way that we sample the world to make it more like our top-down generated predictions. So we can literally choose where to look, where to visually palpate, where to select our information from, so that our behavior, our active engagement with the world, becomes a self-fulfilling prophecy in relation to our predictions. It's in the service of making our predictions come true. And that proves to be a very simple and compelling model for a lot of adaptive and volitional, willful, lawful behavior. We haven't got time to go into it, but suffice to say that this mathematical formalism on top of the known anatomy and physiology of the brain has enormously empowered the interpretation of a wealth of knowledge about neural circuits, both microcircuitry and the macroscopic organization of the brain, the physiology, the role of plasticity, not only in the cognitive neurosciences, but also in trying to understand where these computational and physiological architectures start to go wrong. So, for example, in many psychiatric disorders, this failure of this statistical organ translates into false inference, false beliefs, either conceptual, such as delusions in schizophrenia, or false percepts, such as hallucinations in many organic psychosyndromes, including psychosis. So it's been an important paradigm shift, certainly in the cognitive neurosciences, that is now translating to a certain extent into in terms of understanding psychopathology. It's also been interesting and important in revising perspectives on motor control, on action, and on behavior. Again, I won't go into that, but there is certainly a growing interest in terms of robotics and the way in which we control our movements with our bodies, but also our internal bodies and what that means for interoception and literally gut feelings and emotions and our sense of self. What I wanted to do is just to illustrate for you, numerically, the excitement about this new perspective on how the brain works and how it might go wrong. I've quantified that in terms of the number of citations per year, and you will see, well, perhaps you can't see, but I know, that now, over a very, very short space of time, just a decade or so, if one does, say, a search on predictive and coding and brain, these search terms are attracting thousands and thousands, tens of thousands of citations at an exponentially accelerating rate. I think this reflects the impact that this sort of theorizing is having in the cognitive neurosciences, but I've also been impressed and fascinated by the uptake of these ideas beyond the neurosciences, certainly in philosophy and what this means for the nature of self and the nature of consciousness and the relationship between consciousness, awareness, inference, and self-awareness and self-modeling. And there are now books appearing that are pursuing these themes by friends actually of this university. I've also seen these ideas being taken up in industry, certainly in terms of startups in Silicon Valley and indeed in Europe, looking at these ideas as the basis of generalized artificial intelligence, actually having automata, artifacts that we can play with, we can interact with, that have their own autonomy, do their own active inference, using exactly the principles that have been transcribed from our understanding of how the brain works. And as I mentioned, these ideas are also finding their way slowly and very provisionally into medicine, translational medicine, and I'm highlighting here the notion of something called computational psychiatry, where we're trying to understand, or people are trying to understand, how the brain, in terms of its physiology and abnormal neurotransmitter systems, how that would translate into broken inference, false beliefs, and the symptomatology and the experience that patients come to you and complain of and are upsetting them. So many diverse implications. Let me now return to why I am particularly pleased to be here. There are a small number of excellent academic institutions around the world that are spearheading this initiative. I would put them down in terms of major players, about 5 universities around the world. Most people would put this university in the top 5. I will put it at the top. So, for example, in this field, the contributions of the Donzas Institute has been absolutely remarkable in leading the way in showing this is the right sort of science to do and the advances that can be made if one adopts this very constructive, predictive perspective. Just to quantify that, these are the number of citations over the past 5 years, again using the same search terms, predictive coding and brain, that actually come from your university. I can tell you, you can do the metrics if you want to, but these are an order of magnitude, if not 2 orders of magnitude, more than any other of your closest competitors. It's incredibly impressive. And by virtue of that, you can see why it is a serious pleasure to be here, to be honored by you because of the contributions that your university have made to what I consider to be a very important advance in the neurosciences. So I want to thank you again, not only for the opportunity to celebrate your contributions and those of your colleagues, but for welcoming me into your academic institution. It is a true and great pleasure. Thank you very much indeed.